Hi students, Ms. Vernon here, and today I'll be talking about lesson 4.4, graphs of the sine and cosine functions. If you recall from our introduction to these functions, sine and cosine function are considered oscillating functions. Sometimes students can get confused with these because they don't know where they start, whether it's 0 or 1. Today I'm hoping to clear that up while also talking about the transformations they can take. Let's get started. First, we're going to talk about the graph of the cosine function. I'd like to remind you that each coordinate x, y simply is associated with a sine or cosine value. X is associated with the cosine of different angle measurements. So in our unit circle, we're going to be focusing in on our x coordinate around the unit circle. Now, technically, I could plot all of these values on my cosine curve, and you would see that they are what create the curve or the shape of the graph. However, we're not going to use all of these values. We're going to focus in and only use the quarter turns. This will make more sense as they're nice numbers to graph, as well as they'll connect to the rotation around the unit circle. Next, I'm going to also highlight the fact that when doing any trig graph, we're going to label our x-axis in terms of radian measures. This is because a radian measure represents the walker's view or the outside edge, which is a distance traveled. Let's go ahead and start by filling in our table. So to begin, we have our highlighted cosine values here. And in our table, I'm going to simply jot down our values. So when x is 0 radians, our y value is 1. Our y, or output, is 1 because the cosine value is the x coordinate. At pi over 2 radians, our cosine of pi over 2 is going to be 0. At pi, our cosine value is -1. At 3 pi over 2, it is 0. And at 2 pi, it is back at 1. Remember that the unit circle just continues to move around. So I have a lot of coterminal angles that will allow for my graph just to continue to grow or expand. Coming down to graphing this, I will quickly be able to graph it. Notice that I've labeled my x-axis with radian measures, and my y-axis is going up by increments of 1 on the solid lines. So at 0 radians, I am at 1. At pi over 2, 0. Pi is -1. 3 pi over 2 is 0. And 2 pi is 1. As you can see, I'm going to connect these points, creating this curve. Now, I could continue on these quarter turns, and my graph will continue to oscillate. However, one period of our graph is considered to be 2 pi units long. The reason why is because it takes from 0 to 2 pi to complete one revolution or one time around our unit circle. So we say the period of our cosine graph is 2 pi. Now, to help you remember the order in which the points come, we often teach this with an acronym. Our acronym is high, 0, low, 0, high, or HALA. So high, 0, low, 0, high, representing the location of each of the key points. Now, with our basic function, just a couple quick details. The range is always going to oscillate between -1 and 1, and the domain is all reals. This is considered to be a continuous function because there are no asymptotes or holes that exist. The max is 1 and the minimum is -1. There are no horizontal asymptotes or vertical asymptotes. The thing that I think is most interesting is the end behavior. We say that there is not an end behavior because this function continues to oscillate, so it never heads off in one direction. Let's move on and explore our sine function. So again, as we saw with our cosine function, the sine function is going to come from the unit circle. The sine function is basically found by taking the sine of different angle measurements. It is the y-coordinate on each of the pairs. Again, we're not going to graph every pair. We're going to focus on the y-coordinate on our quarter turns around the unit circle. Writing these into my table to then graph it, I would have sine of 0 is 0, sine of pi over 2 is 1, 0, -1, and 0. The sine function always starts at 0, 0. Then it moves to its high point at 1. At pi, it's back at 0. Its low point occurs at 3 pi over 2, and we finish up at 2 pi, one cycle around the unit circle. Again, just as we saw with our cosine function, I could continue to graph this and graph another cycle. Or I could go in the negative direction, plotting those key points and continuing to graph it. But one period of our sine function is equal to 2 pi. That's the amount of time it takes to complete one cycle. Now, just as we saw with our cosine function, we have an acronym we use to help with this. This one is 0, high 0, low 0. Oh, hello. It's kind of like we're going to Hawaii. So again, oh, hello stands for the order in which we see the changes in the graph. Again, you'll see that the range is sandwiched between -1 and 1, and it is still a continuous function. The sine function also does not have an end behavior because it continues to oscillate. Let's go ahead and move on to talking about transformations of these functions. When we're talking about sinusoid transformations, we have our core transformations we've seen in the past. We have translations left and right, up and down, vertical stretches and shrinks, horizontal stretches and shrinks, as well as reflections. Be sure to note that when you reflect a graph over the x-axis, those cosine value, for example, which is normally high 0, low 0, high, turns into low 0, high 0, low. So when it's reflected, it changes those high and low values. Okay, let's just take a second and have you make some predictions. Here's a sinusoid function or a sine graph, and I have highlighted the A, B, and C and D. And I'm curious which of the above transformations you think each letter represents. Now that you've had a chance to put in your thoughts, I want to highlight one other part before we explore this with more detail. When we have this function, it's important to isolate each transformation. In order to isolate the B and the C transformations, you need to factor the B out of the equation so that each transformation exists on its own. Let's go ahead and take a look at what each transformation does. The first transformation we have is our vertical stretch or shrink. This is going to always be referred to as the amplitude of the graph. We'll talk about this in more detail soon. The B value is a horizontal stretch or shrink, and it affects the period and frequency of the graph. We'll define those again in upcoming slides. C is known as a horizontal shift left or right and is called a phase shift when referring to it with our sine and cosine functions. And last but not least, we have translations up and down. We don't give this a special name, just the A, B, and C terms. Let's provide a little more detail around those terms. So the A value is the B value is going to always represent your horizontal stretch or shrink. If you have a b value of 2, it actually is a horizontal shrink of 1/2. A b value of 1/2 or 0.5 is a stretch of 2. Remember, these are always opposite of what you think will happen. Because the period of each of these functions is normally 2 pi, to transform it, given a horizontal stretch or shrink, we're going to take 2 pi and divide it by the absolute value of b. This is going to allow for us to account for the start and end of one period of the graph. You'll see how we space this out soon. Again, the graphic representation of a period of a graph is the length it takes for one full cycle of the wave to be completed. The frequency of the sinusoid is not something that will show up on an assessment, but is often used in applications. Graphically, the frequency of the graph is the number of complete cycles it takes for a wave to complete in 1 unit of time. To calculate it, it's just the reciprocal, b divided by 2 pi. Again, the frequency of the sinusoid will not show up on assessments, but I just wanted you to know what that was. It will show up on some of your math Excels. Let's take a look at amplitude, or the vertical stretch or shrink. An amplitude of the graph is always found by taking the absolute value of a. Graphically, it's half the total height of the wave. Now be careful, that can be a little confusing. I have a picture for us to look at. In this case, -3 is the a value. When I take the absolute value of it, I find that the amplitude is 3. Notice that the amplitude of 3 would show up from center to top. So top to bottom. Next, that is 3 units long. Notice that the actual total height from top to bottom is actually 6 units. That's why they define it as half the total height of your curve. Let's jump into a couple examples to help you better understand this. In this graph, I have an a value of 3 and a b value of -2. The a value of 3 is going to represent a vertical stretch of 3. It tells us that the amplitude is 3. That would represent the high and low of our graph. The b value is -2. This is actually 2 transformations. It's a reflection over the y-axis, because it's attached to the x, and it also is a horizontal shrink of 1/2. This horizontal shrink of 1/2 is going to take our 2 pi period and cut it in half. So to calculate the period of this graph, we take 2 pi divided by the absolute value of -2. 2 pi divided by 2 is pi. That means the time it'll take to complete one cycle is pi units. Let's go ahead and take a look at another example. In this example, we're going to describe the transformations and then graph our function. So first, I noticed that we have an a value of 2. The a value of -2, is going to represent that we have an amplitude of 2. It also is going to show that we have a reflection over the x-axis. The b value in this case is a little tricky. It's actually 1/2. Sometimes students don't see that right away. So I usually encourage them to think about, if I pulled the 2 out, it would be like saying 1/2 times x. The b value of 1/2 will affect the period of this graph. The period of this graph will be 2 pi divided by 1/2. Simplifying this complex fraction, I need to multiply the top and bottom by 2 over 1. When I do this, 2 pi times 2 is 4 pi. Now that I have my amplitude and my period of this graph, I'm ready to graph it. I'm going to use our acronym shortcut for cosine to organize my work. That's high, 0, low, 0, high. Now, because it is reflected over the x-axis, I know that my high point becomes my low point, and my low point becomes my high point. I also know that the high and low points are going to be at 2 and -2. So because this is low, it's going to cross on the y-axis at -2. Because this is high, it's going to cross at +2. And because this is low, it will cross at -2. I also know that my period of my graph is 4 pi, which means I'm going to start on my x-axis at 0 and end at 4 pi. Figuring out the in-between parts isn't so hard. Half of 4 pi is 2 pi, and half of 2 pi is pi. Now I can start to see my pattern. 0, pi, 2 pi, this must be 3 pi. Now that I've got my x and y's set up, I can go to my graph. So at 0, I'm going to start at -2. At pi, I'm at 0. At 2 pi, I'm at 2. At 3 pi, I'm at 0. And at 4 pi, I'm at -2. Graphing this, my scale's a little stretched, so you might go, does that really look like cosine? But it is. Remember, it's a reflected cosine function. Once you graph one, it's easier to continue graphing the rest because you have your spacing already created. And you can graph the remaining part. There you have your graph of your transformed cosine function. I've got one more for us. In this one, I see that we have a translation up 4 units. We also have a vertical stretch of 2, which is going to affect our high and low values. Again, we have a cosine function. Notice that there is a b value of 1. So that means the period of this graph is going to be 2 pi divided by 1, or just 2 pi. So it's a normal cosine function translated up 4 units and stretched vertically. That means I can create my acronym, high, 0, low, 0, high. And I can place in my x values based on the period, which is 2 pi. So I start at 0, I end at 2 pi. Halfway in between is pi. Half of pi is pi over 2. So 1/2, 2/2, 3/2, 4/2 reduces to 2 pi. For my highs and lows, I'm going to have it be at 2 and -2. Remember, the 0 is just 0. Now, there's a couple ways to address this idea of up 4. One of the most popular is I see students draw in what they call a translated axis. So they draw in a dotted line that represents this up 4. Then when they go to graph their highs and lows, they base it off of this translated up 4 value. So for example, at 0, I needed to go 2 units above this. At pi over 2, I'm going to be on that red dotted line. At pi, I'm 2 units below. At 3 pi over 2, I'm at 0. And at 2 pi, I'm 2 units above. Now I've graphed my first period of this graph. From here, I can continue to graph this function to get a better idea of what the graph will look like. Now, you can continue to fill this in so that it fills the whole graph, but we're going to stop at this point and say it's good. So there you have it. I just graphed two functions and described transformations on a third. Tune into class for more information around these functions. Have a great day.